Okay, so get out your homework. Homework 3. Thank you very much, Diggers. And the video for that is posted. I sent it to your email last night. But it's the video is kind of bad quality. I didn't post it to YouTube. There was a lot of chatter. Dot 1 shout out, not quite as quiet and contained as Dot 7. So love them, but they're a little bit harder to video. Okay, so if you look up here, we've got our answers through 1 through 5. So take a quick peek at what you have here. So for 1 through 4, we're finding linear and angular speed, very similar to 1 through 4 on the guided note sheet. So the first one we have a radius, and then in the second one we have a diameter, so you had to divide this number by 2. Very, very similar to the notes sheet. Are there any questions on 1 through 4? Number 5, we had a conversion. It was our first conversion. We had millimeters per minute, and we needed to convert it to meters per second. So we had to divide 1 meter by 1,000 millimeters in order to cancel them. Divide 1 minute by 60 seconds in order to cancel minutes.
You're fine with us leaving like the first 4 in like pi, right?
Right. So if you had 1090 pi over 1 minute,
okay,
that's fine. All right, we're all good through 5. I'm not seeing any objections. And then this is 6, 7, and 8. 6 is way up there. Pull that down. 6 and 7.
Yep.
Did you get to this bit here?
Yeah.
So you must have done something along the way in the conversion that messed up that number. So we wanted to go from inches per minute to miles per hour. So we had to cancel. We had to cancel minutes out. That gave us hours. Then we had to cancel. Did you do that in between the 12 inches per foot? Maybe something happened with your division. Because that's 5,280 feet per mile. There aren't 12 feet in a mile. Whoopsies. It happens. It totally happens. And like I said in class, you'll be getting a list, like whenever you're going to have to do this work on an assessment of any sort, quiz or test, I'll give you a list of like, there's 60 minutes per 1 hour, there's 5,280 feet per mile, there's 1,000 millimeters in a meter. Like, I'll give you that.
I have a question on the graph. I need to do that.
The radians per second. So remember with angular speed, it's how, like, what is the rotation of the central angle over a unit of time? How is the central angle changing over time? And so that's when we multiply by 2 pi radians, because 2 pi radians is the same as 360 degrees, or a total rotation. Do you remember that from our unit conversion? So with our unit conversion, we had 2 pi radians is the same thing as 360 degrees. So we had pi radians is equal to 180 degrees. So what this is saying is if I have an angle and I'm rotating 180 degrees, that's 180, or I could also write it as pi radians. If I'm going 360 degrees or a full circle rotation, that's 360 or 2 pi radians. And a radian is just the measurement. It's a measurement of the angle when the radius is equal to the intercepted arc. You don't need to know that, but you need to know that 1 full rotation is 2 pi radians. This is just a unit of angular measurement, just like degrees is a unit of angular measurement. So when I'm calculating angular speed, remember it's that central angle is that 2 pi, which is 1 full rotation, times however many revolutions I'm doing. So I'm revolving 33 times per minute, and I'm revolving 2 pi radians 33 times. So that's how I calculate that. And then you get to 66 pi radians per minute, but I want it in radians per second, so then I have to figure out what my conversion would be so that my units cancel, and I'm left with seconds. So I don't cancel the numbers, I'm just canceling out the units. Does that make a little bit more sense? Okay. And this is different than our linear speed, where we're multiplying by 2 pi r times the number of revolutions. Because for the arc length, or the linear speed, I have to do 2 pi r, which is my total circumference around the circle, versus 2 pi radians, which is the total angle measurement as a round circle. So that's why I multiply by 2 pi r times the number of revolutions when I'm measuring distance, and I multiply by 2 pi when I'm measuring angle measurement. Okay. I'm on duty from like now until Monday morning, so like hit me up.
Why are you on for so long?
Just the way the cookie crumbles. Alright. So we got 8 through 10 that we can have on the board.
Wait, I did do that right.
Oh, I did that same thing.
Oops.
What?
I got the feet.
This?
Yeah.
That's okay. Now you probably won't do it again.
Wait, but how'd they get that right?
I don't know. You must have done something right.
Oh, I see it. I wrote
James, do you have your homework out? Nice. You good with these?
Yeah.
Okay.
Good.
Good? Through 10? Alright. Cool.
Oh wait, sorry.
That's
You
okay.
can fix all the ones with feet in there. Or with
I'll
arms.
also, this weekend what I can also do is I can post the answer keys for all the homeworks, so that way if you want to go through these, you can, if you just want a second glance at them. Does that sound good? Alright, so now we have 11, and 11's like the toughest it's going to be, but 10 and 11 went through our new, 9, 10, and 11 actually went through when we went, what is another way to find linear speed? Normally we find it arc length over time, but then we went through the conversion. The arc length is really radius times theta over time, which is really radius times angular speed. So we calculated angular speed, and then we multiplied it by the radius to give us our linear speed.
I did it like the normal, like the other way, because I did the other one on like this one. I don't know why, I just liked the first one better.
Yeah, so these are two methods of solving for it. It's just, what this is trying to get you to do is identify where you can swap things out. So like identifying, oh, arc length is radius times theta. Oh, this looks really similar to this. Like, it's just starting to recognize when you don't have all the information, what you actually can plug into a problem. Like, so you can do it a couple of different ways. But these would work the normal, the first way that you learned how to do it too. Because it gives you all the information. It gives you radius. It gives you revolutions. You can, figure it out from there. All right, any other questions? We're feeling good? All right, cool. So we are going to start something kind of brand new. We're going to move away from circles for a little bit, and we're going to move into triangles. So this whole unit that we're going to do until the end of the winter term, and then where did I put the papers? Did I put them over there? Did I put them right here? I did. So the whole unit that we're doing between now and the end of winter term, and then a little bit when we come back from winter term, is based on triangles and circles. And the stuff with triangles, some of it will be new. Like some of the stuff we'll cover will be new, but some of the stuff you will recognize. It's not going to be all brand spanking new. Got that SOHCAHTOA stuff going on.
SOHCAHTOA.
SOHCAHTOA. And hopefully because trigonometry has so many applications in the real world, hopefully this is stuff that is a little bit more relevant to grasp. Like you can actually see things like in this classroom that are triangles that you can measure using these formulas. There's just a little bit more relevancy with the topic. All right, so Aiden, why don't you read us that first bullet point to the right of trigonometric functions?
Trigonometry is the study of the relationships among the side and angle measures in a triangle.
Great. So trigonometry, study of the relationships among the side angle measurements. Can someone read the next bullet point, please?
Trigonometric ratio compares the lengths of two sides with respect to an acute angle theta in a right triangle.
Great. So if you look to the left of those bullet points, you have a triangle that looks like this. This is a right angle triangle because I have a right angle or something that's 90 degrees. To remind you what 90 degrees is, it's when two perpendicular lines intersect themselves. So this forms a 90-degree angle, and this acute angle theta is an angle that's less than 90. So I'm representing this angle theta and the 90-degree angle with this little square. So these are the visuals I use. So the trigonometric function is defined by ratios, and so our ratios are given by side lengths. So we have, if we're looking at theta, so we're not looking at the right angle here yet, but if we're looking at theta, this is our opposite side, and this is our adjacent side. So these are just vocab words, opposite, adjacent. It says this right here. And then our hypotenuse is determined by where the right angle placement is. So our hypotenuse is always the side length that's opposite the right angle. And so our functions that we're using are these sine, cosine, tangent, cosecant, secant, cotangent, and these are determined by ratios. So you might remember SOHCAHTOA for sine, cosine, and tangent. Does anyone remember what those mean?
Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent.
Trying to keep up.
Yours?
Okay. And so to break this down even further, what this is saying is that this function of theta, which we're going to do more with later, but sine of theta is equal to the opposite length of the angle theta, opposite over the hypotenuse. It's not saying that the angle measurement itself is the opposite over hypotenuse, but that the sine of that angle is equal to that ratio. So if I was to say, what is theta for this? Like if I was to give you a triangle, like a 3, 4, 5 triangle with theta here, and I was to say, what is theta equal to? Based on your knowledge, you might be able to solve this, but it would not be equal to 3 over 5. That theta would not, but sine of theta would be equal to opposite over hypotenuse. Does that make sense? And then cosine of theta is equal to adjacent over the hypotenuse in regard to theta. Tan of theta is opposite over adjacent. And so that next column, cosecant, secant, and cotangent, those are what are known as reciprocal functions.
Cosecant is CSC.
Oh yeah, sorry, not cosine. Thank you. So cosecant is the reciprocal of sine theta. So what would that be equal to? The reciprocal of opposite over hypotenuse would be nice. Secant is the reciprocal of cosine. What would be nice? And cotangent is the reciprocal of tangent, which is Nice. And so below you can write those. There's a box below that says because cosecant, secant, cotangent ratios are reciprocals, they're called reciprocal functions. So you can write below cosecant of theta is equal to 1 over sine theta. Secant is equal to 1 over cosine theta. And cotangent is 1 over tan theta. And this will make it easier moving forward when I'm giving you examples with specific ratios that are written out. Make sure that this works. Okay, that works good enough. All right, so let's look at number 1.
Can I get a paper?
Oh, yeah. Whoop. So we just filled out the first 6 boxes here, so you can use this. Right here, fill out that chart. So let's look at number 1. We've got a triangle here, a right angle triangle.
That was such a good triangle.
Is it?
I think so.
Thank you, Elisha. You know, I'm very good at drawing.
Good triangle.
Yeah, I'm just doing my best. So we got a 5, 12, 13 triangle here. With right angled triangles, what is another formula you know with side that I can use to solve for side lengths?
Area. No. Base times height.
That's area of triangles. Pythagorean's theorem. So when I have a right angled triangle, I can also, like, if you look at number 3, there's a missing side length there, but it's a right angled triangle, and this only works for right angled triangles. It doesn't work for any triangles that aren't right angle. But you can do a squared plus b squared equals c squared, with a, b being the side lengths, and c being the hypotenuse. So I could do 5 squared plus 12 squared equals 13 squared, would give me this right angle triangle. All right, so for this one, it simply just wants me to fill out the 6 trig ratios. So I've got sine theta, cosine theta, tan theta, cosecant theta, secant theta, and cotangent theta. So sine, remember, is opposite over hypotenuse, so what is my ratio here? And I'm looking at theta, remember. I'm not always going from the corner, from a certain corner. What is my opposite length? 12. And what's my hypotenuse? 13. Cosine is equal to adjacent over hypotenuse. What is my adjacent length? 5 over, what's my hypotenuse? 13. Tan is equal to opposite over adjacent, so I have my opposite is 12 over 5. And then what's really nice about these is I can literally just go 13, 12, 13, 5, 5, 12. I can just flip them. And if you want to, you can go back through and be like, all right, what's my hypotenuse over my opposite? What's my hypotenuse over adjacent? What's my adjacent over my opposite? If you really want to go through and double check. So I want you to try to do number 2 with the thought in mind that you cannot have a square root in the denominator. So you're going to have to simplify further. If you have like that 4 radical 5, if that's in the denominator, you're going to have to multiply by radical 5 over radical 5 to simplify. Around and look when you feel like you're done. Yep, so that's adjacent because it's the side that's next to it, but it's not the hypotenuse. Because this 13 is always going to be the hypotenuse.
So like the opposite would probably be
The opposite would be this 12. This is what's directly across. So like here,
so like
That's
for
gonna
this
be-
one,
for secant, that would be hypotenuse over adjacent. So that would be 13 over 5. You guys got it? Feeling great?
No.
Okay.
Okey doke.
Okay.
Got it.
like, do you know this?
No, you have to multiply. This one's would be no, this one's 8.
Okay, so for number 2, let's label our sides first before we jump in and do the math. What side is my hypotenuse? What's the value of my hypotenuse?
It's 4 radical 5.
Yep, so this is my hypotenuse. Oh, that looks great. So this is my hypotenuse. What is my opposite?
8.
Opposite
Oh,
theta.
sorry, 4.
Yep. And what's my adjacent then? 8. So it's always easiest, especially when the triangles start to get all wonky and we're not in like the standard drawing of a right angle triangle, to look at where my right angle is and then mark your hypotenuse first. And know that we're identifying the adjacent and opposite sides based on where this theta is in the triangle. Like it would be different if I had a theta here, right? Then my opposite would be 8 and my adjacent would be 4. Yes.
Is it always the same like order of things like
For these, the ratios, yeah, the ratios are always the same. Yeah, opposite hypotenuse, adjacent hypotenuse, opposite adjacent, and then the reciprocals. It's always the same ratio for these. So for this one, for sine, my opposite over hypotenuse, I have 4 over 4 radical 5. And unfortunately, because we're working with square roots here, because of Pythagorean theorem with right angle triangles, you're going to be getting this a lot. A radical in the denominator, at least for 1 or 2. At least for 2 of the ratios. So remember, you can't have this. We learned this in the very beginning of the fall. So I have to multiply by radical 5 over radical 5. So this becomes 4 radical 5 over 4 times radical 5 times radical 5, which is what?
20.
What's radical 5 times radical 5? Yeah. And then what's 4 divided by 20?
Oh.
1, yeah.
Oh,
Well,
I mean 1
yeah.
fifth. Yeah.
yeah, so it'd be radical 5 over 5 would be my final answer for that one.
Right. So you have to do the math for every single one. You can't just find out what.
Not every single one.
Because can you just figure out what 4 radical 5 is, and then you just plug that in for everything? Because in all reality, it's going to be the same, right? Unless it's on the, like, whenever it's on the bottom. It's like
Yeah, so like for cosine of theta, this is adjacent, so this is 8 over 4 radical 5. So again, I would do radical 5 over radical 5, which I know would give me a denominator of 20 again.
Yeah.
And then it would be 8 radical 5, and then I can simplify that to what? What goes into both 8 and 20?
4.
4. So it would be 2 radical 5 over 5.
Right.
Yeah. So as long as you know what you're getting to here, but then re-simplify your numerator,
Yeah.
that's the key, is your numerator is going to change always.
Right.
So I wouldn't say one size fits all for this. I would say go through the motions. And this will get, because we haven't done this in a while,
Yeah.
this will get more, like, more practice we get, the easier this will get. Like, this is probably, like, for some of you, like, oh, God, I thought I left this. Like, I'd never have to do that again. Sorry. And then tangent is my opposite over adjacent. So I've got 4 over 8, which simplifies to 1 over 2.
But so when you go to the next ones, you can't have a radical on the bottom again, right?
Right. So you can either flip this and then simplify, or you can go in and you can say, all right, this is 4 radical 5. It's hypotenuse over the opposite, 4. So then those 4's cancel, and I'm just left with radical 5, which is what you would have gotten if you had gone through this process anyway. So if you know that this is going to be in the numerator, I would almost, unless you're really comfortable with flipping and then resimplifying, this way is always going to be faster for me, so I would choose to do it this way.
Gotcha.
But you have to be comfortable with flipping the ratio, to look and be like, okay, this is hypotenuse over opposite. This is hypotenuse over adjacent. So I know that's going to be radical 5 over 2. And then cotangent's nice, it's 2 over 1, which simplifies to 2.
OCOs.
How are we doing with this?
It's okay, I guess.
It's okay? You okay? It's okay, I guess. Yeah. I mean, it's like, I think this stuff's fun. I don't know. I think it's kind of fun. It's like composite functions. Those are like real fun. No one liked those. I could tell from the test, but you know what? They're gone now. Unless you still have the test to finish.
I'm working on it.
All right, I know. It's not your fault. For some of you, we have agreements. So, all right. So for number 3, let's do this. Actually, why don't we do number 4 together, and then you can do number 3 with your buddy, because number 3 is a little simpler than number 4. So for number 4, we have this funky triangle. I'm going to try and draw it. A right angle here. I'm never going to get it right. 6 radical 3, 6, and then a blank. All right, so let's identify these sides really quick so we know what we're solving for. So which one's my hypotenuse? Aiden.
The hypotenuse?
The bottom. And we're trying to solve for that. So then I can choose either, where's my theta here? Theta's here. So which one's my opposite? Yep, 6 radical 3, so this is opposite. And then this is my adjacent then, just by default. All right, so we have to solve for that missing side length. So what's my Pythagorean theorem again? Which is my opposite squared plus my adjacent squared over my hypotenuse squared. So we're solving for this. So a squared, so let's do 6 radical 3 squared plus 6 squared equals c squared. So what is 6 radical 3 squared? Really? Let's do it not as a decimal. Oh, we got 36 here. Yeah. And then this would be
It's 12.
Hmm?
It's 12.
c squared is 12.
C squared is 144.
Yes.
And
So
C-
how did you get to this? What did you simplify this to?
What you do is you square it, which is going to get rid of the square root, but
Mhm.
it's also going to square the 6. So it's right.
So what did you get?
36 times 3
Yes.
108.
Great.
Wait, so how
It's
do
going to
you
get you to 144.
So when you have 6 radical 3 times 6 radical 3, that becomes 6 times 6 times radical 3 times radical 3. So that would become 36 times 3. Because radical 3 times radical 3 just simplifies to 3. Or you could look at it like this. You could look at it like 6 squared times radical 3 squared. And then our square root and our and our exponent would cancel. Because really,
Would it be
when I have
36 then?
it would be
6 times
36
6.
times, it would be 6 times 6 times 3. Because realistically, when I have 6 radical 3, I could rewrite it like this, right?
Yeah.
And if I'm multiplying it times itself 2 times, it's just doing this.
Yeah.
So 6 times 6 would give me 36. Radical 3 times radical 3
Yeah.
gives me 3. So that gives me 108.
Yeah.
Yeah.
I was just like, wait, why are we doing this? And then I
Number
looked at
4,
paper, and
yeah.
I was like, oh, there's a missing number.
Yes, our hypotenuse is
Fun.
missing. So we got 144 equals c squared. So just like Sam said, we take the square root, and we got that c equals 12. So now we have all the pieces. So Maria, do you understand now how this simplifies to this and not 10.4? I think you did. Did you do?
Well, I didn't have a calculator, so
But did you? You must have not put the parentheses correctly. I don't know where you would have put them. Maybe you did 6 squared times radical 3. Maybe.
you want some color?
Yeah. Well, radical 3 squared would be 9, or it would be 3.
Wait, 12?
So that would be 18.
Wait,
Because 12 times 12 gives me 144.
no, but like,
Oh,
what's
I have a
like,
question.
oh no, that's, yeah. Yeah.
Yes.
So instead of doing, when we do it 6 to the square root of 3, can we just do, like, for example, for this one, 108 over 12?
No, because 108 over 108
Oh, that's
is a
squared.
squared. Yeah. So Hunter is jumping ahead to our ratios here. So sine opposite over hypotenuse. So we've got 6 radical 3 over 12. How can I simplify that, Eek?
That would be a half.
So radical 3 over,
Oh, 2.
nice. Cosine is adjacent over hypotenuse. So we've got 6 over 12 adjacent over hypotenuse. Kristen, how do I simplify that one?
1 over 2.
Nice. So tan is adjacent, opposite over adjacent. 6 radical 3 over 6. James, how would I simplify this one?
I can't read.
6 radical 3
Oh,
over 6.
divided by 6.
Divide by 6, which would give me radical 3. Great. So now when I get to my cosecant, my secant, and my cotangent, I can go 2 over radical 3, then multiply by radical 3 over radical 3, so that gives me 2 radical 3 over 3. Secant of theta, I would just take the reciprocal of this, so it would be 2 over 1, which equals 2. And cotangent of theta, this is
Radical 3 over 3.
nice. So cotangent of theta would be 1 over radical 3 times radical 3 over radical 3, which, as Kristen just said, simplifies to that. Do we have any questions about how we got to these 3 numbers by simplifying
And
them?
I did for keep going up. That one?
Mm-hmm.
For all over. No. What?
So what I did is
No,
I
not
took
for that one.
I took the simplified version of it. Because it would be 12 over 6 radical 3, which would simplify to 2 over radical 3. So I took the reciprocal of my simplified ratio. Just like here, this is the flipped version of this. So if I simplify my sine theta ratio, I can use the simplified version. All right, so try number 4 on your very own. I'm going to take a look at the back.
We did 4.
Oh, try number 3 on your own. Thank you, Chris. Did you get it?
I'm just
Try number 3, please. Let's stay hyped. Got 3 more dots.
Nuh-uh.
so fast. I got one more No one said it. The
I
size
got
is
it. I got it.
So you do it like tomorrow? I have like
He's out.
writing. Literally writing.
Doesn't matter what That's what for A, B, and C.
It's not for A and B, but for C, yes. C has to be the hypotenuse, which is the angle, which is the side opposite the right angle. Nice job, Neil.
You got hurt today. So if you take any of the
Man.
Bye.
Okay, I'll go over that with you.
Yeah. I heard it.
This one,
Yeah.
put the
Me neither.
hypotenuse in there.
Wait.
But you want it to be, you want
Yeah,
it to
you
be
select minus.
20 over
So this is 21.
or 20.
So you got 141.
So your hypotenuse
This
is
is
correct.
400. So
But we're going with this
this
theta.
minus this.
So what is the opposite side?
29.
No, what's the opposite?
Yeah. And then you have to minus 400, right? We got this. See,
So don't you add these?
no, because if you add these two, the square root, you would got this. But this is hypotenuse.
Oh, so we just
Miss Young,
Uh-huh.
are we writing the answers right now?
I'm not writing answers right now. I was just drawing.
Did I get it right?
No, the whale tail down flat.
No. But close. Very, very close.
Really?
You had your C squared. You had your hypotenuse. So it would be 20 squared
I want to do
plus
something.
B or 20A squared plus 20 squared equals 29 squared.
It's weird to like cut out. Get that.
You guys good?
Wait, I have a question.
I'm almost done.
So
Okay.
like basically, how can you like transfer everything?
This is a height. And the opposites,
So you know that's the hypotenuse. So that's
Yeah.
adjacent, these two,
So C squared is
A,
zero.
B, C. So
Oh,
basically,
you subtract. You subtract.
Then you can choose A or B for it.
so basically,
Why do you subtract?
Yes, always
this
there's
terms
terms.
A squared
Carson, is that you?
plus B squared
Oh, dude, I just totally messed that up.
B, C. But we have this and we
Alright, so,
have this.
Elijah, which one is my hypotenuse?
Minus
29.
Thank you.
A equals B.
Aiden, which one is my opposite?
Subtract.
20.
This is
No. Blank.
Blank. And then that leaves 20 as my adjacent. I always do adjacent last, so adjacent is like always last in line. So for this one, I would do 20 squared plus B squared equals 29 squared. So my hypotenuse should be my C term.
How do you know which one's A, B?
You can just, it doesn't matter. You can go like adjacent is A, but because I'm adding these two things together, it doesn't matter where it is. You're going to be subtracting this from here anyway. So then you're eventually going to get into, when you do B squared equals 29 squared minus 20 squared, you get B squared equals 441. Whew.
Damn.
What is the square root of 421 or 441? 21. Sorry, I said it. Oopsies. So this is my 21 opposite. All right, so you should have, for sine, you should have 21 over 29. For cosine, 20 over 29. For tan, 21 over 20. Then 29 over 21, 29 over 20, and 20 over 21. Capiche?
Capiche?
Capiche? You got it? Cool. All right, so flip it to the back. We're gonna. I know. So for the last 2 minutes of class or 3 minutes of class, we're going to go over what I would like you to be able to translate to your homework. So when I give you a ratio, you're able to identify what that means on a triangle. So if we look at tan, I'm just going to get 5 started for you. If we look at tan on number 5, we have tan theta equals 7 over 24. What side lengths did this give me for a triangle?
7.
Yeah, but what are those side lengths? What is tan? What is the tan ratio?
Opposite over adjacent.
Opposite over adjacent. So we can draw a triangle here, right angle triangle. I'm going to do it like this because this is just the standard form way of doing it. So my opposite length is 7, my adjacent length is 24, and I'm looking for my hypotenuse. So then based on this information, can you calculate your other trigonometric ratios?
Yeah.
Awesome. So now let's look at number 6. I just want to set you up for this so that you aren't like,
Adjacent over hypotenuse.
yes, so cosecant of theta,
Oh wait.
we've got 37 over 12, which is equal to our hypotenuse over opposite. So if I draw, again, this standard triangle here, I know this is my hypotenuse. So this is 37, because this is my height. And then if I'm looking at this theta angle, this is my opposite, so that's 12. And then this is my adjacent, and I'm trying to solve for that one.
Bada bing.
Oh, okay, that makes sense.
Are there any questions about solving for those? So 7 and 8 are very similar to those with cosine. Cosine would be adjacent over hypotenuse. Secant would be hypotenuse over adjacent for those values. Your homework will be, let me just make sure I give you the right number. Problems here. I would like you to do 1 through 12 on your homework, please. And we will go over special, I call them special triangles. Yeah, so we'll go over special, yeah, we'll go over special angles next class.